Artificial neural networks are built from densely interconnected set of simple units where each unit takes a number of real valued inputs, possibly the outputs of other units, and produce a single real valued output which may be input to many other units. Neural network learning methods provide a robust approach to approximating real valued, discrete valued, and vector valued target function. McCulloch and Pitts introduced the first mathematical model of a single neuron called as a perceptron. A perceptron is a type of artificial neural network which takes a vector of real valued inputs, calculates a linear combination of these inputs and outputs +1 if the result is greater than the threshold value, -1 if the result is less than the threshold value. This is the architecture of a single perceptron. A perceptron consists of real valued inputs, here x1, x2, x3, and so on up to xn are the inputs. Each of these inputs, they are associated with the weights w1, w2, w3, and so on up to wn, where wi are the weights, or they can be considered as real valued constants that determine the contribution of input xi to the perceptron output. The weights and the input, they are multiplied, and here we have a unit that is called as a linear unit, that is the summation, where this is going to give the output z equals to sigma of I equals to 1 to n wi into xi plus b. This is called as the linear unit of the perceptron. This sum obtained by this unit, it is processed through the function that is called as an activation function. This activation function, it is going to trigger the next neuron to some percentage, and these activation functions, some may be linear and some may be non-linear. Through this activation function, we get the output. The output of the perceptron may be either 0 or 1, or it can be either -1 or +1. So the output equals to the value z, it is processed through this activation function sigma of I equals to 1 to n wi into xi plus b. So the output of the perceptron is +1 if this value is greater than 0, -1 if otherwise. Here we have one more value that is called as the bias. The bias is present only when the data is not balanced. Whenever we need to increase or decrease this summation value, then we had a bias. So we have input xi, wi, they are real valued constant. Finally, the perceptron produces the output, which is 1 if this is greater than 0, -1 otherwise. This sum is processed through the activation function. We have different types of activation function. To name few, we have the first type of activation function that is called as step function. As I told, these activation functions, some are linear, some are non-linear. Step function, it is a linear activation function. When this z is processed through this activation function, that is sigma of z equals to, it is 0 if it is less than 0, 1 if z is greater than or equal to 0. The activation function possible output is in the range 0, 1. So we will be having either 0 or 1. If the z value is less than 0, we have 0. If it is greater than or equal to 0, the output from the perceptron is what? That is 1. The second type of activation function, it is called as sine function, sometimes signum function. When the linear unit value is processed through the activation function, that is sigma of z equals to returns 1 if z value is greater than or equal to 0, -1 if z is less than 0. The range is, that is possible outputs are in the range -1, +1. Coming to the representational powers of the perceptron, these perceptron, they are represented in a hyperplane decision surface in n-dimensional space of instances. It is nothing but the instances, they are represented on the hyperplane. So the instances are nothing but these points. They're represented as a hyperplane decision surface in n-dimensional space of these instances. Perceptron can represent all the primitive Boolean functions like AND, OR, NAND, then NAND and NOR. With this, unfortunately, some Boolean functions cannot be represented by a single perceptron, such as XOR function. How can do perceptron classify? So basically, we use neural network to classify the instances or the training examples. So how can do a perceptron classify? Suppose you consider we have these instances that are represented on a plane. Then we have a perceptron which consists of two inputs, X and Y. The weight associated with the first input X is Wx. Weight associated with the Y is Wy. We have the bias value. Initially, we consider bias value equals to 0, Wx equals to minus 0.5, Wy equals to 0.5. So what is the aim of the perceptron, or what the perceptron has to do? So we are into identifying a decision boundary that is going to classify these instances. So we are into what? Identifying this decision boundary. Since we are using a single perceptron, so it is going to linearly classify the instances. Fine. So when we find this linear or this decision boundary, so whichever the points are classified here, we can consider this as +1. Here, these are classified as -1, or these are classified as 0, or these instances are classified as +1. So we are into identifying this decision boundary. So if these points, they are separated by a linear, or if these points are separated linearly, then these data points are called as linearly separable decision boundary. So how can do a perceptron classify? Here is just a simple example. Initially, if we consider these points, so this unit, it is going to do the summation, that is X into W into X plus Y into Wy plus of bias value. So this equation, or equation for this decision line, it is always considered as W vector into X vector, which is equal to 0. So this can be 0. So it is minus 0.5 X plus 0.5 Y plus of 0, which is equal to 0. So it is 0.5, which is equal to 0.x. So y equals to x, which is linear in nature. So we are identifying this linear decision boundary. So perceptron is all about learning, or learning the perceptron involves choosing the values for the weights, that is W0, W1 up to Wn. Therefore, the space H of candidate hypothesis considered in perceptron learning is a set of all possible real value vectors of weights. So we are into identifying this decision boundary. So if these data points are separated linearly or classified linearly, they are considered as linearly separable sets, and some of the points are not separated linearly, they are considered as linearly not separable data points. So whenever we have this of equation here, you replace with any value of X or Y, the perceptron is going to classify that instance either to this group of the instances or this group of the instances. So we are into learning the weights of the perceptron. So we need to learn the weights of the perceptron. So that is what we are into in learning what? In learning the perceptron. So how to learn the weights for a single perceptron? So the precise learning problem is to determine a weight vector that causes the perceptron to produce correct plus or minus 1 output for each given training example. One way to learn an acceptable weight vector is to begin with random weights, then iteratively apply the perceptron to each training example, modifying the perceptron weights whenever it misclassifies an example. This process is repeated, iterating through the training examples correctly. So we have two rules for learning the weights for a single perceptron. The first one, it is called as the perceptron rule. The second one, it is called as the delta rule.